Hello grade 11s and welcome back to another video. Thank you so much for making it so far. This is an investment into your future. You're going to be using your November marks, so your end of grade 11 marks, in order to apply for university. But also remember, next year in grade 12, you're going to be writing your exams on questions involving Newton's law. So Newton's laws will be tested again. So thank you very much for taking yourself and your future seriously. Let's get into question 1.3. This question says a constant force F is applied to a 6 kilogram block to move it up a rough surface. So again, we take note, it's going up the surface and the surface is rough. Why are they telling us this? Well, because if it's rough, we have friction, and if it is moving up the incline, then we know friction is always in the opposite direction to the motion. Important information to take note of. They then say that the surface is inclined at 60 degrees to the horizontal, and fortunately for us, that is included in the sketch. Now they say force F, which is parallel to the incline, moves the block up the incline at a constant velocity. Now, if you watched the previous video and paid very close attention, you'll remember there are two cases where the net force is 0. Case number 1, when the object is stationary. Case number 2, when it is moving at a constant velocity. Now the question says, the block experiences a constant kinetic frictional force of 12,25 newtons. Okay, so we know that this force is kinetic, of course, because the object is in motion and they mention it, and it has a magnitude of 12,25 newtons. Question 1.3.1 says, draw a free body diagram showing all the forces acting on block Q. So we would like to draw a free body diagram, and unlike the previous question, this is not for nothing, this is for marks. So we're going to draw it as accurately as we possibly can. Fortunately, no marks will be awarded for the length of the arrows, but we do check to see if you've included an arrow at the end, if they are away from the dot, and of course if they're in the right direction. So firstly, this object is on a surface. If it's on a surface, it means that a normal force is being applied, and as always, the normal force acts perpendicular to the surface. So we're going to draw in our normal force like that. The object is moving up the incline because there is a force which they have called F that is pushing the object up the incline. We don't draw the force there because the arrow may not point to the dot. It needs to point away from the dot. So we draw it on the other side. The friction force, we said, is going to be down the incline. Friction is always parallel to the surface. Normal force perpendicular to the surface, friction parallel to the surface. And always, gravitational force is going to be straight down your page. Always straight down. Whether the object is on an incline or on a horizontal surface, Fg is always straight down. Okay, now let's say that you didn't draw it this way. Sorry, my words got tied over there. Let's start off with this. Where are you getting your marks? You're going to get 1 mark for your normal force, 1 mark for the force F that's being applied, 1 mark for friction, and 1 mark for Fg. If you included any additional marks will be subtracted. You're going to be penalized. But I know that some of you, instead of drawing your free body diagram like this, prefer to use the components of Fg. So if you are drawing in components, often we start off like this using a dotted line. So you may have started off drawing in your perpendicular component, which would be like that, perpendicular to the surface, and then your parallel component, which is always down the incline. Now, this is how you check to see if you've drawn your components correctly. Firstly, they're going to meet at a 90-degree angle, like the 90-degree angle over here. That's number 1, they're meeting at a 90-degree angle. But secondly, Fg parallel is always down the incline. You're going to remember this because you never slip up an incline. You always slip down an incline because of FG parallel. That is what causes you to slip when you walk up or run up an incline plane. Now, unfortunately, you are not allowed to draw the components together with the resultant, even if you draw dotted lines. So if you drew it this way, I'd like to encourage you to go and cross that out neatly. And then you're going to redraw your free body diagram as I'm going to do on the left-hand side of my page. So over here, we're going to draw in the normal force as we did. So everything else stays exactly the same. We have the normal force up the incline, we have F, we still have the friction force, but then we're going to draw in the components. Don't draw them in at, what are they called, angles. They must be parallel to the surface and perpendicular to the surface. So in need, draw the dot bigger. And then over here, in the same direction as friction, we have FG parallel, and perpendicular to the incline, we have FG perpendicular. If you do it this way, you're going to get 1 mark for the forces over there and then 1 mark for both of your components. So either you draw the resultant or the components, not both. I prefer to do a rough sketch like this somewhere because it's going to help us with our calculations at a later stage, but it's completely up to you. Now that we've done that, we move on to question 1.3.2. This question says calculate the magnitude of force F. Force F is this force that is acting up the incline. We know that we may only add together forces that are parallel to each other. So what is parallel to F? We have the friction and we have FG parallel. So we can set up as Newton's second law or even first law if you want to, but we normally call it Newton's second law equation. So we're going to say F net is equal to ma. Automatically we know this is 0, and that is why I said Newton's first law. We know that the acceleration is 0 because this object is moving at a constant velocity. We must remember to choose one direction as positive. And in this case, I'm going to choose up as positive, so down will be negative. But you are welcome to choose it in the opposite direction. Just be consistent. So here we have F minus the friction, which is kinetic friction, minus Fg parallel. That is the forces. We're trying to find the actual force F, so we're going to leave that as F. The friction force was given to us. They gave it to us as 12,25, so we're going to substitute that in, 12,25, and we still need to calculate Fg parallel. So Fg parallel is a component. I'm going to go to the sketch that I crossed out because it's just so helpful, and that is why I said I always include it somewhere in my rough work. We know that this angle is the angle that we're going to find over here, and here is a right angle triangle. When you're dealing with the right angle triangle, we use trigonometry, where this is the hypotenuse. Here's our angle, so this is the opposite side, and this over here is the adjacent side. So if we're trying to find the opposite side, we're going to say sine theta is equal to the opposite, Fg parallel, over the hypotenuse, which is Fg. In other words, Fg parallel is equal to Fg sine theta. I like to remember that when I'm trying to find the opposite side, I'm going to use the resultant. So Fg multiplied by sine, because sine is for opposite. And if I'm trying to find the adjacent side, Fg perpendicular, I'm going to use cos. So Fg cos theta. It's unnecessary for you to show these workings. So if you remember that it is sine, you just write that down. Fg sine theta. Fg is equal to mass times gravitational acceleration. The mass of this object is 6. G is a constant 9,8, and we plug in sine theta, where theta is the angle of the incline, or the angle that the incline is making with the horizontal. When we plug this into our calculators, we obtain an answer of 50,9222 9. Okay, so remember, I like to round it off to 5 decimal places or more, and this is going to be measured in newtons. So we're going to include that newtons just in case. So in the place of FG parallel, we put in 50,92229, and we say that this is equal to 0. Now all that we have to do is solve, and when we solve, we find out that the force is equal to 63,17 newtons. And this is the final answer to this question. So marks, we have 4 marks, and they're going to be allocated as follows. You're going to get 1 mark for your formula, 1 mark for substituting your values on the left with the correct directions, 1 mark for substituting on the right hand side the 0. If you did it on the left, that's also okay, and 1 mark for your final answer. We are only looking for the magnitude of the force, and therefore we do not need to include direction, which is up the incline. Now we go on to question 1.3.3. It says the angle of the incline is now increased to 75 degrees. How will this affect the magnitude of the velocity of the block as it moves up the incline if the force F acts on it remains constant? Choose from increases, decreases, or remains the same for 2 whole marks. If it's going to help you, go and draw, because drawing is going to give you a better idea of what's going on. At first, we had an object on an incline, and I'm going to draw that incline less steep like this. There's our block. And then what happened is that we increase the incline. Now I am exaggerating over here, but it's just to emphasize the point. In both cases, we have a downwards FG. And that FG has exactly the same magnitude because the block has exactly the same mass. So there's my FG. If I draw the components in the first case where the angle is 60 degrees, here is my perpendicular component, FG perpendicular, and here is my parallel component, FG parallel. Now let's go to the 75 degrees. Again, this is not drawn to scale. I've exaggerated everything to help it make sense to you. And we have FG perpendicular. Already you should realize we went from a long FG perpendicular to a smaller FG perpendicular. And when we draw an FG parallel, there it is. We went from a short FG parallel to a longer FG parallel. So what is happening is we have a force being applied, force F, that has not changed. It's still parallel to the surface and has the same magnitude. But in this case, we have an FG parallel that is smaller than in this case where the FG parallel is quite long. Since the FG parallel in the case on the right where we have an increased angle is longer, we know that this force, which is causing the object to move towards the right, has a force that opposes it. And therefore, as a result of this force, the object, this FG parallel which has increased, the object is going to slow down. The correct answer to question 1.3.3 is therefore decreases. And for writing down decreases, you're going to get 2 marks. But grade 11s, if you were asked to explain this, then you would have to mention that as a result of the increased angle, the incline is steeper. Since it is steeper, FG perpendicular is going to decrease, while FG parallel is going to increase for the same FG. Therefore, we have more force in the opposite direction to the motion, and as a result, the object is going to slow down. So 2 marks for decrease and grade 11s. This brings us to the end of question 1.3. So we finished off question number 1 on Newton's laws, but there's one more law that we're going to explore in this set of videos, and that is Newton's third law, and not one law, but 2 laws, Newton's third law and Newton's law of universal gravitation. We're going to take a look at that in question number 3. So please, question number 2, grade 11s, in question number 2. So please be sure to join me in question number 2.